Thanks for having me. I'm going to speak on the possibility to enhance the ensemble Kalman filter using a spatial model. To motivate this research, this is actually a practically oriented research. It's motivated by the well-known fact that the sample covariance matrix, which is implicitly or explicitly used in the ensemble Kalman filter, is actually a very good estimate of the true covariance matrix, but only if the ensemble size is much greater than the size of the covariance matrix, which is, of course, never the case in our problems. So in high dimensions, the ensemble Kalman filter never contains enough information to specify the prior covariance matrix accurately enough. So we have to supply some additional information to the problem, that is to regularize it. The existing regularization techniques are well known. Here it's their list. The common imperfection is that they're largely ad hoc, which requires extensive and therefore expensive tuning, especially in a practical system. Besides, as for covariance localization, it can reduce noise at small distances where the noise is the strongest, and it has other deficiencies as well. Mixing with climatological covariances is not scale selective. The noise in these sample covariances is the sampling noise is reduced exactly to the same extent as the valuable pole-dependent signal. We propose to introduce a spatial model estimated online from the prior ensemble that is abandoning the sample covariance matrix, directly use the ensemble members, and use the spatial model to specify the prior covariance matrix. Potentially, the advantage of this approach is that it allows to optimize the use of both the ensemble and the so-called climatology. To do so, we are going to place a prior distribution on the prior model, that is a hyper-prior distribution, which goes beyond the mean B matrix, which is the mean of this actually distribution, and use a Bayes estimator to optimally combine the ensemble data and the hyper-prior distribution. The model, we require from the model that it should be non-stationary, of course, to capture fault-dependent structures. And we aim at a non-parametric model to not to impose specific shapes on spatial covariances. We rely on the general process convolution model, that is a filtered white noise. Here, alpha is white noise, x and y are points in the domain of interest. By default, it's the sphere. W is a convolution kernel. The space discrete counterpart of this equation leads to the well-known factorization of the covariance matrix, which is often used to efficiently precondition the analysis equation in operational analysis solver. But this model is completely general. It's too general because it's not unique. Given the B matrix, there are infinitely many W matrices, and having one, you can multiply it by a orthogonal matrix and obtain another W matrix. So to obtain a unique solution and to make the model identifiable from the ensemble, we have to constrain it. First constraint is to assume that the convolution kernel is locally isotropic, that it's the convolution kernel depends on the distance between 2 points and additionally on the location x. The resulting spatial model is on the left, and its spectral space form is on the right. Here y is the spherical harmonic, alpha, Lm are the mutually uncorrelated zero mean unit variance, complex variate random numbers, and sigma L of X is actually a Fourier transform of the kernel with respect to distance, or spectral transform on the sphere. The square of this sigma L function is what we call the local spectrum, because in the stationary case it reduces to the conventional spectrum. The second constraint is more technical. We assume that these sigma L of X are non-negative. If these two constraints are met, then the model becomes identifiable. But still, the model which is reproduced here has far too many degrees of freedom. That is these functions sigma L of X. So we introduce two further more fundamental constraints. First, we note that the convolution kernel as a function of two arguments has two length scales. One L is with respect to distance, which determines the ordinary length scale of the random field in question, and the other is lambda is the length scale which the kernel varies with respect to location. We call this the non-stationarity length scale. And the constraint is that lambda is much larger, much greater than L. And this leads to so-called local stationarity, and under which we can approximate our random process by a non-stationary process by a stationary process locally in space or in time. And the final fourth constraint is that the spectral functions are smooth functions of the wave number. So they are smooth functions actually of both the wave number and the location. Now we have to estimate this sigma L of X function, which are the parameter of our model. What we do is we apply a series of bandpass filters to ensemble perturbations, the spatial filters. And each filter isolates a spectral band. Here is the example of their spectral transfer functions. And if the above constraints are satisfied, then the variances of the filtered fields are approximately satisfy this equation. That is, their linear combinations of the local spectrum. Each scale, each filter isolates a specific wave number band, and so the variance becomes proportional to the mean local spectrum over the wave number band number J. We have a low resolution spectral space, low resolution observation on the spectrum. We can write it down as a linear. So all we have to do is just to connect the dots, because the spectrum is assumed smooth. So these low resolution observations should be sufficient for us to estimate. What we do, we replace variances by their sample counterparts and solve this linear inverse problem. Actually, we tried to first we tried some conventional regularization techniques to solve this problem, but we didn't obtain impressive results in the analysis, and therefore we resorted to neural networks, and these neural networks gave very good results, and we started thinking what we have done, and we understood that actually we have built an approximation to a general Bayes estimator. What is a Bayes estimator? We have a parameter in question sigma. We should have a prior distribution. We have the likelihood of the data given the parameter. We have a general point estimator. We specify a loss function, whatever we wish. And then we compute the so-called Bayes risk, that is the expectation of the loss function over the joint distribution on the parameter and the data, and minimize it over the space of all estimators. And this and the minimum is the bias estimate. Of course, with our high-dimensional problems, we cannot tackle multidimensional non-Gaussian densities, so we resort to Monte Carlo. And instead of the prior density, we assume we have a sample for it. Instead of the likelihood, we make use of the generative data model. That is our spatial model, which is generative by construction. And we parameterize the point estimator using a neural network. So it's a function of the data we have, and psi is the vector of neural network parameters, that is weights and biases. Finally, in the bias risk, we replace the expectation by the sample mean. And we obtain this equation in which we replaced the general loss function by the quadratic loss function. And then we realized that actually this minimization process is nothing other than the standard neural network training. And it appears that this estimator already has a name, the neural bias estimator. So we use this neural bias estimator. And that was, informally, that was a kind of relief, because it appears that those almighty neural networks can be made just part of our theoretical and practical toolbox. So a few experiments, some results. First, we tried this technique on static analysis on the sphere. Here, in this case, we had access to the true prior distribution of these sigma LFX, that is parameter of our spatial model. And this we did when we did have access to the true prior, to the true prior hyper prior distribution, then the results were just exceptionally good. Here you see the normalized root mean square errors for in the greenish curve is the ENKF. The bluish is very kind of variational analysis with the static mean B matrix, and they're hybrid in brown. And magenta is our analysis based on our filter, our technique as a function of ensemble size. And you can see that the advantage was really big. But this is the best what we can get from this technique, because we had access to the true hyperprior distribution. Then we tried this approach on a more realistic problem. We call it a sequential assimilation on a one-dimensional spatial domain on a circle. Use the model described in this paper. The spatial grid had just 120 points on the circle. We had to introduce some proxy to the hyperprior sample, and still we managed to obtain very good results even in this more or less realistic, quasi-realistic situation. Here again, these four filters: variational, static B filter, ENKF in green. By the way, the shading is the 90% confidence interval, and the brownish is the hybrid, and here is our filter. What's interesting here is that our filter performed better even for the ensemble size of 160, which is very large ensemble compared to 120 points in the grid. And the second point worth mentioning is that our filter performed significantly better than the hybrid, which means that it is capable of using the climatological climatological distribution, climatological information better than the hybrid filter, hybrid EN-var filter, which takes a linear combination of localized sample covariance and in the climatological metrics.
2 minutes.
Okay, just my last slide. So to summarize, we regularized, we proposed a technique which regularizes the ensemble Kalman filter using a spatial model. We assume that we postulate that prior uncertainty in the filter is governed by a spatial model, which is non-stationary and non-parametric. In this, the spatial model is estimated at each simulation step using a neural-based estimator, which is to be trained before. The estimator optimizes the use of both ensemble members and the hyperprior distribution on the hyperprior distribution. In simulation experiments, our filter performed substantially better than the baseline stochastic ENKF and filter with static covariance metrics and their hybrid. And we are currently working on a multi-resolution framework in which it seems that the technique should be computationally tractable. The computational complexity should be growing linearly with the number of the grid points. So it should be affordable to us to finish this work and come up with a practical system. So you can have a look at our preprint and the program code. So thank you.
Great, thanks so much, Mikhail. Great talk. We have a few questions online. So first from Peng Zhang, how to select the filter frequency H for the filter?
Filter frequency, what do you mean?
I will let them clarify, I'm not sure. I'll go to Tobias's question because it may be related actually. So Tobias asks, says, thanks for the great talk. How do you choose the spectral bands used in the bandpass filters and how sensitive are your results to this choice on slide 10?
It's an interesting question because first we just selected them manually, but then we understood that the width of the bandpass filters spectral transfer function should depend on the ensemble size. The greater the ensemble size, the wider spectral transfer functions we can afford. Those wider spectral transfer functions, importantly, correspond to a shorter impulse response function of their of the bandpass filters. As a result, we can capture more localized non-stationary features. So in the limit, we can resolve whichever non-stationarity we wish using more and more broad spectral transfer functions.
Great, thanks. Peter Jan says, do I understand correctly that you solve the machine learning problem at every grid point? I seem to miss something.
Yes, exactly. This is the primary point, because otherwise we couldn't hope to make this technique practical and operational. Yes.
All right, well, I think those are all the questions online, but maybe you can check the OPED after, just in case some follow-ups come in. Thanks, Mikhail.
Thank you.